In this video I'm going to go through the results of the paper on isolated umbilic points, which recently appeared in a journal dedicated to Caratheodory. So the general topic of the paper hinges around the following conjecture, an old conjecture of Caratheodory from 1923, almost 100 years. So the number of umbilic points on a convex sphere in Euclidean 3 space is greater than 1. G0 here is the flat metric, of course. And here we talk about a sphere, we don't mean a round sphere, of course. This sphere is a topological 2-sphere. Probably has to be at least twice differentiable to define umbilic point, so we could throw that in, but that's the standard conjecture. So what we're going to talk about is a counterpoint, which is theorem 2 of the paper, which says that there are metrics on R3 arbitrarily close to the flat metric for which the conjecture does not hold. So there exists a convex sphere in R3 with a metric that's not the round metric, but it's arbitrarily close to it, and not the flat metric, but arbitrarily close to it, but has exactly one umbilic. And the explicit construction of the metric is the proof, essentially, of the metric and the sphere with exactly one umbilic point. A related conjecture from the 40s is an index bound on isolated umbilic points, which states that the index of an isolated umbilic point on a convex sphere in Euclidean 3 space is less than or equal to 1. So this would imply the Caratheodory conjecture for closed spheres, because it must have at least one umbilic point. However, and they must add up to 2. In any event, we'll talk about that in a bit, but this is one route that implies the Caratheodory conjecture. And once again, we have a counterpoint to this result in theorem 1 of the paper, which says there are metrics on R3, again arbitrarily close to G0, for which umbilics can have any index. And in particular, you can have ones that violate Hamburger's index bound. And again, the proof is by explicit construction. Okay, so to kind of give you some motivation or guidance as to where how to interpret this result, let me turn to a quick sketch of the proof of the Caratheodory conjecture by myself and Wilhelm Klingenberg, which also in a weak index bound, another paper by ours later, which also proves a Hamburger-like index theorem. Anyway, the proof is essentially splits into 2 pieces: the Fredholm regularity of an associated boundary value problem, and then the use of mean curvature flow to show existence of solutions to that. Taken together, then these imply the conjecture. The mean curvature flow itself has split into 2 pieces, naturally one which is the interior estimates needed to ensure long time existence, and the boundary estimates required to ensure that no information or nothing is lost at the boundary. So as of now, start of 2021, these 2 parts have been accepted and appeared, and this third piece, well, hopefully someday soon. It's also worth noting that, in fact, exactly the same methods prove a conjecture of Toponogov on complete surfaces, again in R3, which is there as a preprint. The references here are in the back of the paper, so you can follow the details in those. Which, by the way, the Toponogov conjecture is also related to sits within a larger conjecture of Milner going back to the 60s, I believe. In any event, let me just talk a little bit about this as a motivation. One of the key things here is the proof of the Caratheodory conjecture in this part, the Fredholm regularity of the boundary value problem. The critical part here is the size of the isometry group. So the isometry group is important here. In fact, without that, you would not have Fredholm regularity of the boundary value, most likely. So one thing from this one could say is that the reason the conjecture is true is actually the size of the isometry group. You need a big enough isometry group to fix a point, essentially. In any event, the corollary, if this is the interpretation that you want to take away from this proof, is that it should not hold for any nearby metric with no isometries. So, in other words, a generic metric will not satisfy the Caratheodory conjecture or the local index bound either. Okay, so this is what you would take from this proof, and this is exactly where this research originated. If this were true, it should be possible to construct nearby metrics where they have no isometries, but they're very close to being Euclidean, and yet they have counterexamples to both these conjectures, and that's what we do in the paper. Okay, so what I'm going to do is give a very brief background in classical surface theory to explain particular umbilic points and how they arise. So let's start out by considering a surface in R3 and the Euclidean metric. We can take G0. In fact, a lot of what I say here goes through for any Riemannian metric you can take, and we're going to be doing deformation, so we will need that. In any event, the basic idea is that if you have a surface in R3, that you can determine its bending or its shape in R3 by its second fundamental form, which is a 2x2 symmetric matrix. It looks a bit like the second derivatives. At a point you can reduce it to the matrix of second derivatives of a graph function if you want to think of it that way. So it's like a matrix of second derivatives. Because it's symmetric, you can diagonalize it and you get eigenvalues and the eigendirections, principal directions and principal curvatures as they're referred to. And these determine the amount of curving in the kind of the maximum amount of curving and minimum amount of curving that you do if you were to move off a surface. Move along the surface from a point. So every surface then has a pair of orthogonal foliations called the principal foliations. These are you have a direction at each point and you patch them all together, you'll get a curve. The principal foliation, you'll get two of them, they're orthogonal, and they won't be defined where these two eigenvalues are equal to each other. So these are exactly the umbilic points. So when the two curvatures are equal to each other, well then in fact your eigenspaces degenerate from a pair of lines to in fact the whole space, and so you have a singularity at this of this foliation at these umbilic points. If your umbilic point is isolated, then you have a natural idea of a winding number, which is that you can map out and measure the turning of the principal foliation about an isolated singularity, and this is well defined. It's only an eigendirection, so in fact it's not oriented, so in fact it's a z/2. It can go through a half turn. In fact, generically it's a half. Generically it's either plus or minus a half. And on a closed surface, if you have a sphere, for example, the full, if you add up all these indices, you get the Euler number of the surface. In the case of the sphere, this is 2, so this is why you must have at least one umbilic point, because that has to add up to 2 on a sphere. So the kind of pictures that we have here gives you a typical picture. Here's your triaxial ellipsoid, has 4 umbilic points, each have index 1/2, so this is kind of a generic situation in some way. Then if you impose more symmetry on it, in fact these two umbilic points at the top come together, so for a rotationally symmetric surface you have an umbilic point on the top of index 1 and an umbilic point of index 1 on the bottom. And then when you try and bring these together, if you're trying to dispute the Caratheodory conjecture and say that we can put these two together to get an index 2, the problem is that you get a singularity in the surface. So this is what goes wrong. You don't get a nice smooth surface. And you can construct ones with rather weak singularities, but there must always be a singularity, it seems, when one attempts this by hand. Okay, so this is the background to the Caratheodory conjecture. Comes from classical surface theory. There's one slight technical tool that will help in some of the discussion later, which is the following. So if you have a surface S in any Riemannian manifold, in other words, got a metric of any sort, positive definite, but any Riemannian metric, you can let E0 be the unit normal vector field, and E1 and E2 be the unit tangent vectors along this surface S. And then of course your second fundamental form is a derivative. It's the covariant derivative with respect to the metric in the x direction of the normal, and taking the inner product in y. This is a symmetric matrix in x and y. Standard classical differential geometry tells us this. And this is your second fundamental form. Okay, so what I want to do is actually take this second fundamental form and I want to project it onto a complex frame, a null frame. So this is a complex combination of the two vectors. It's like conformal coordinates, if you like, on the plane. So it's complex E1 plus I, E2, and E1 minus EI. Anyway, so these are standard null frame introduced in a definite situation. And when you take these two complex vectors E plus and E plus and you put them into the second fundamental form, you get a complex quantity which we'll call sigma, and a real quantity if you put in E plus and E minus, because it's symmetric. It's like taking a conjugate and you get the same thing. So rho is a real function. So these are functions. It's a complex function and a real function which pick up the information of the second fundamental form just projected into these null frames. What's interesting here is that the link with our underlying thing is the following, is that the norm of this second fundament of this complex quantity is the difference between the eigenvalues, in other words, the curvature. So this is 0 precisely at umbilic points. So this will characterize where umbilic points occur. This is the mean curvature, or minus at mean curvature. We don't use that very much, so we won't refer to it in the future, but for completeness you can see you've encoded the information of the eigenvalues and directions in these 3 real quantities, or 2 complex and 1 real. Okay, so at sigma equals 0 we have umbilic points, and just a little bit more than that, we as a computational tool, if you have some kind of complex coordinate z and z bar on S, and if you compute your surface and you end up with something that looks like this, so this sigma, well, the argument of sigma is exactly the index of the umbilic point. So in some ways what you have here is the norm of sigma is determined by the difference between the eigenvalues, and the argument determines the foliation. And when you have something like this, you have an isolated umbilic. Here we have h times z bar. H is a real non-zero function, and then this vanishes when z is 0, as n and m are positive numbers here. So then at z equals 0 is an isolated umbilic point at that point, and the index is exactly this half of the m minus the n. So you can compute, if you have something in this form, you can compute what the umbilic points and their indices are very straightforwardly. So that's a useful thing we'll see now in this explicit construction that we're about to undertake. Okay, so let's cut to the chase and then talk about the first theorem of the paper, which is the Theorem 1, and it states that for all epsilon greater than 0 and k, which is a half integer, there exists a smooth Riemannian metric on G on R3, and a smooth surface in R3, such that 2 properties, that S has an isolated umbilic of point of index k, whatever that k is, you can do that, and you can make it arbitrarily close to the flat metric. And here is your L2 norm. L2 norm here means you're integrating the difference over the whole of R3. Okay, so you can perturb the metric very small in this norm, and you still get something that violates the Caratheodory conjecture. Sorry, this is the Hamburger index bound. In fact, is what we're trying to construct here. Okay, so let's look at the basic idea. So if you take x1, x2, and x3 in R3 as your standard coordinates, and you take these complex coordinates z to be x1 plus I, x2, and t to be x3, then our metric is just dz bar, and dt squared. Just to make life easy, because we're going to work with some simple constructions. So the surface we're going to think of, S, is going to be given by t equal to 0. It's a flat plane. In the flat metric, it's just a plane. And it's totally umbilic, so all curvatures are 0 at that point. All right, but all of this is with respect to the flat metric. So what we want to do now is to keep the same surface, but we're going to perturb the metric. So our S is not going to change. It's going to be the surface t equal to 0. So fix this S, and we're going to deform the ambient metric to the following. So G is your flat metric, plus this diagonal term, or off-diagonal term, I should say, dz dt and db dz bar dt, where b is a function on z bar, and it's a complex valued function. Okay, so there are 2 things we're going to mention, is that if you keep this b small, this metric will be Riemannian. So when b is 0, obviously you just have the flat metric. But if you keep b small, it will stay being a Riemannian metric, and, well, the difference between it is just the total integral of this beta. What's more, for the surface t equals 0 in this metric, this is the key quantity. So this is the complex function that determines the index and the existence of umbilic points. And what this says is that if you take, just for this surface t equal to 0, with this metric, general metric, the solution, this being equal to 0, will tell you exactly where the umbilic points are, and the winding number of this thing here will tell you the index if it's an isolation. Okay, so this quantity contains all the information, and it's just a del it's like a del bar operator. It's in this representation, it's del of beta bar. Okay, so these two propositions are just direct computations. So now let's see how we compute, how we construct the metric that we need. So we take the surface t equal to 0, and the metric that we're going to choose is exactly z to the n, z bar to the m, right? This is just for our beta. We're choosing this beta now, in a neighborhood of the origin. You take two annulae, or 0, or 0 to or 0, or 0 to or 1, and here we put in a bump function to kill it off. So again, we just want to localize this construction around the surface. So here we're going to kill it off outside of a radius of or 1. Okay, so lambda here is a scaling, which we'll use at the end in order to make it as small as we want, and it's clearly possible to do this. So phi is our bump function, and so by proposition 2, when we compute what the sigma is, well, it's just the derivative, or in the origin, in the neighborhood of the origin, it's just this part here. So when you differentiate it, you get a real function times something like this. And so the origin is an isolated umbilic point, and the index is given by, well, it just depends what n and m you chose. That will give you them. So what that tells us then is that this proves statement 1. This tells us that we have an isolated umbilic point of whatever index you want. Just choose your n and m, you can get positive numbers, and you can get positive or negative indices of any half integer. So that proves statement 1. Now this whole construction here was independent of the scaling lambda, and that's the second part, which is to show that we can actually just bump the metric away. We can certainly make it localize it on the surface, put it that way. We can localize it on the surface here. Here's our or 0 and or 1. We've localized it on the surface, but our metric has been changed for all values of t. Right, so the thing is, we now want to kill the t direction. So we introduce another bump function psi on the matrix, which will kill it, so that it'll be Riemannian. It'll be in fact flat, the standard flat metric after a certain point, and you can choose any one you like there. And in doing that, then you still haven't changed the scaling which we have introduced initially. So when we write down the difference, it's an integral of something like this, and our scaling can be done at the end to make that as small as we like. Hence we've constructed an umbilic point. I mean, the idea, I guess, in my own head, the way I think about it is I fix the surface in R3, and then I kind of perturb the metric. And in perturbing the metric, I'm using it and molding the perturbation of the metric to construct a principal foliation of any signature at isolated umbilic points, whatever you want. Now, of course, it will also create umbilic points in other places on the surface in order to, I haven't got much control away from this point, but all I need is in a neighborhood of this point. I just need control of it, and that's enough to ensure counterexample to Hamburger's index theorem. Okay, so now for theorem 2, let's again look at the statement. Again, it follows an analogous path. So for all epsilon greater than 0, there exists a smooth Riemannian metric G and a smooth convex sphere S in R3, such that it has exactly one umbilic point on this surface S, and it's arbitrarily close to being the flat metric. Okay, so again, the construction is similar, except this time we're going to move to spherical polar coordinates. So I'm going to take a radius from the origin, r squared, and I'm going to take a spherical element, and the spherical element here is given by a complex coordinate on the two-spheric psi. So that's the standard metric in these coordinates. And the surface I'm going to take is going to be a sphere. So instead of taking a plane, which I did in for the theorem 1, I'm going to take a sphere in this case. And again, it's totally umbilic. It's not flat, but it's the two curvatures are equal to each other, so a round sphere. Okay, but again, that's all with respect to the flat metric. And now what I'm going to do is going to perturb this by deforming the metric. And once again, I'm going to deform by a complex function, which a function of two variables, this time a function of this xi, it's called xi bar. And it's just here, it's an off-diagonal element to the standard flat metric. So I've done this here in coordinates, some coordinates from stereographic projection from South Pole. You can also do stereographic projection from North Pole, and you can go between one and the other using the antipodal map. So you need to extend this over the sphere, which you can easily do. And again, this is for any function beta. So Again, if beta isn't too big, well then it's Riemannian. If you make beta too big, the diagonal term, off-diagonal term dominates the diagonal term, and you get a Lorentz metric or degenerate. But anyway, you can keep Riemannian as long as you don't make it too big. And again, the difference between it and the flat metric is exactly this norm. Hence these terms out here that allow us to write this in a simple way. Once again, we need for the case, what if you fix the surface or 0 in this perturbed metric, or equals or 0? And the answer is again, well, that you can compute that from the second fundamental form that this complex function, which determines umbilic points and their winding numbers, is exactly del of psi, with it's got an extra factor in there, as often happens with these kind of spherical coordinates. But in any event, it's like a del bar equation on a complex function. Now, again, we can now try and prescribe the beta and work backwards, and that's precisely what we do. So for the next part, we proof of our theorem, final bit. For theorem 2, so if you have or equal to or 0 and you perturb the metric, but this is the specific form that we take for beta. And again, you can extend it across infinity by switching coordinates. There's a canonical way to do that. What you find then is for this one, the norm of sigma is never 0. So in other words, there are no umbilic points except possibly at infinity. If infinity is a nice smooth point, well then all the umbilic points are at infinity. If you switch then to antipodal coordinates, you do compute it and you find that it is a real function times xi bar to the 4th. And this is exactly an umbilic point, an isolated umbilic point. H here is non-zero. So the index at infinity is exactly as you expect it to. So what we have constructed now is a surface, a sphere, with a single umbilic point of index 2. It has to be by the Euler number. Okay, so finally, to make the distortion globally small, so again, we want to bring this arbitrarily close. Again, what you can do is you bring in a radial bump function this time, so you want to again kill this off, you know, at great radius, because outside of the sphere you don't really care, or inside you don't really care what happens. You can go back to the round metric. So again, you scale by lambda, and you can make this distortion globally small. So again, you fix your surface, and you just do your perturbation in this little collared region here, and you can do it arbitrarily small, and you can scale it by this lambda, which was free from the start, to make it as close as you like to being the flat metric. Okay, and with that, if you've made it this far, thank you for the attention.